Thank you very much for the kind introduction. Yeah, that's exactly what we intend to present to you today. So I guess you can hear me well, right? Good. As we saw before, we had a lot of different materials, but I want to present you metal as a material for 3D printing. And as you can see, we are working in the cubic meter scale, so quite large. And also compared to the other things that you can see on the fair. So we want to work in 1 meter by 2 meter scale, for example. The process that we developed for us is the Macro-SLM. So some of you will be familiar with selective laser melting, and we just scaled everything up. And in the following 15 minutes, I will present to you who are we, why do we need this new Macro-SLM process, and how do we use it. And in the end, we will show you 2 use cases of how we and you could implement it in the industry. 2 of my colleagues, Professor Streeck and Martin Erler, are also present if you want to have a chat afterwards. Okay, so we are a public university. We are a University of Applied Sciences in the east of Germany, close to Chemnitz and Dresden. It's a quite small town. And we are having many colleagues who are now for 50 years already are working on many different fields of laser applications. I think not all of you are familiar with laser applications, so I will just give you a brief rundown of what we can do with all the laser technologies. For example, we can have bionic surfaces, we can have macro treatments such as laser welding and so on. We have microprocesses such as laser structuring, as you can see on the left-hand side. Then also we have pulse laser deposition to apply coatings, for example, to steel tools. We have a lot of simulations, measurements, and then bottom left, we have additive manufacturing, which is the main part today. Also, we have development of digital optics for EUV, for example, biophotonics, and then, of course, we also build a lot of our laser setups ourselves, so we have a lot of experience in that. So the question is, why do we use a larger process, and why do we need a larger process? The thing is that there's many different applications for this kind of process. I want to explain to you one specific use case. So you can see on the left-hand side a facade that can be custom built with many different angles and so on. And each of those nodes that is connecting the facade has to be usually built by hand, which is a very time-consuming and therefore expensive process. So we were working together with colleagues from Leipzig who are doing the design with a parameterized design of each of those nodes. So we're writing an algorithm that automatically creates all the CAD files for each of those nodes, so thousands of nodes. And we, on the other hand, can then use these files to produce the physical nodes that you can see on the right-hand side. We made a first design study, and we were using the default selective laser melting, as you can see also the machines here on the fair, to print some of those nodes. And you can see it on the right-hand side, it's open, so you can look inside to see the topological structure. And it was still printing 80 hours, and it cost material only, so only the gas and only the powder itself still cost 1,000 euros. And that is first too slow, and it's still too expensive. So we wanted to scale everything up to make it cheaper and faster, while still being able to have all the design freedom of the selective laser melting. So what exactly is the Macro-SLM process? So I guess some of you will be familiar with the selective laser melting, or SLM. In theory, you can see on the top left, you coat a layer of powder, then you melt it with a laser beam, and then you rinse and repeat for thousands of layers until you have your finished part. In the end, you will also need to do some post-processing like cutting it and cleaning. And this allows you a very large design freedom because you have the powder layer that is supporting your structure. So you can print channels, you can print bridges, and you don't have any restrictions regarding the complexity of your design, which is a large advantage. There's also some disadvantages because usually you will need complex laser scanning devices and so on. And also the powder is very expensive because it's, let's say, 60 micrometer powder. So you end up with a very expensive process in the end. Also, the build rate is rather low. So if you want to build very high and very wide, we need cheaper processes that are faster.
Hey.
What's that? Sorry. Over here. Oh. 1 second, please. Yeah, okay. So a different process that we use to combine with this default SLM is the DEE, the direct energy deposition. Basically, this is a much faster process. And here you don't use a powder bed, which is the largest difference. That means you also use less powder and you can use much more energy. That leads to a near unlimited size. For example, it's similar to the concrete examples that we saw before. And also very high build rates of up to 1000 cubic centimeters per hour compared to the 17 cubic centimeters that we saw before for SLM. But the problem is, as you can see on the top, you always have to build one layer on top of the other. So there is no protective powder bed. So you don't have any of the channels or the more complex geometry that you could build. But as you can see on the bottom right, there you can build very large, for example, tanks for aerospace and so on. And what we wanted to do now is to combine the advantages of both the default SLM, which is the design freedom, with some of the aspects of the direct energy deposition. So for example, we wanted to have an affordable machine with affordable material such as powder. We wanted to have a very high build rate that is comparable with the direct energy deposition. And also we wanted to have large scale parts. And these aspects together were combined to create a Macro-SLM. So how do we do that? We still want to keep the powder bed to allow for complex structures. We have a gantry setup, so no optical scanners. So I guess you're all familiar with gantry setups. It's quite simple and therefore cheap design. Also, we use coarse material. So the material is at least 200 micrometers in powder size. So it's, let's say, 10 times larger than the default SLM powder and therefore also 10 times cheaper per kilogram. And also we use a single high power laser beam. So there's other approaches with, let's say, 20 or 30 small laser beams that are all acting parallel, but that's very expensive. So we use just one very powerful laser beam. Okay, let's go to our setup. Here you can see the prototype setup that we built at our facility. And what's quite impressive is that it's 2 by 2 by 1 meter of build chamber. So that's many scales larger than the usual SLM machines that you can find. We are having a laser power of up to 8 kilowatts in the continuous wave. And as you can see, we also have the gantry system. So if you look on the picture on the right, you can see my colleague for scale. So it's a very big machine. And the thing is that usually you would lower down the part while it is built. However, that's not possible because if you completely fill this machine, it will be 20 tons of steel powder. So you don't want to move this 20 tons around. Instead, we will move the laser device up. So the machine bed is stationary, while then the recorder and the laser processing head together will move upwards on the 4 parallel Z axes. And also they are combined with an XY positioning stage. So that's a very simple optical design. We also have very variable spot sizes. And yeah, I think I mentioned all of the important parts. Now I would like to show you the machine in action. This is our video. Is there no video? Excuse me, is there a video in the slide? Right, thanks. Just a second, please. No. Well, then I guess it's without video. Okay, maybe I can explain as such. So you would have seen in the video how the laser machine is moving around. And then the recorder first is applying the powder layer. And then, which is about, let's say, 1 millimeter high, so very, very large. And then the laser head is moved by the XYZ axis across the sample. to treat a part, and then the next layer is applied, and then the process is repeated. So let's move on.
Yes.
To the results that we got. So since we are also a research institute, we want to look very well into the mechanical properties. So how are the structures that we actually build? How reliable are they? And I think you are aware that the most important value for this is the relative density. So how much percentage of the volume is actually filled with metal and not with air or pores or gases, for example, because that would lead to mechanical failure. And in general, we got above the 99.5% threshold, which is the usual threshold. So you could say that we are actually printing completely dense cubes, for example. So you can see on the left-hand side some walls that we printed with different laser powers and different laser sizes. So you can see there that on the left-hand side, 1.8 millimeter walls were printed with 2000 watt of laser power, which for normal SLM would be very much, but for us it's still a low amount. And then we had in the center some 4 kilowatt of laser power, and on the right-hand side of the walls it's 8 kilowatt of laser power, which is already quite a lot. And you can see there we were able to build 5.5 millimeter wide walls. So basically you could then design your product to be built with, let's say, 5 millimeter walls, and you can imagine how fast that would work. On the right-hand side of the slide, you can see one of the test cubes in the cross-section. So you can see there that it is completely dense, or at least close enough. And with this process, we have a theoretical build rate of 1,300 cubic centimeters per hour, which is more or less also the value that you saw earlier for the direct energy deposition, and about 50 times higher than the default SLM. And for stainless steel, for example, that would be 10 kilograms of stainless steel built per hour. As I mentioned before, the mechanical properties are also very important. And on the left-hand side, you can see the table with the datasheet values from the norm. So we can see that we have to have a tensile strength of at least 500 megapascal. We were measuring 615 megapascal with our tensile probes. And interestingly, also there was no difference between the vertical and the horizontal plane. So there's no anisotropy, which is also very important if you want to apply loads to your samples. The yield strength had to be above 190 megapascal, which was measured at 320, so that was also above the requirements. And the elongation at break had to be at least 25%, but we were having 45%, so it was also ductile enough. So you can say that the mechanical properties of our samples were passing the norm, which is already a very good sign. Also, we did some fatigue tests, and at 1 million load cycles, we had a fatigue strength of about 300 megapascals. Something that is new and not similar to the default SLM is that we have a large degree of design freedom, because as you saw before, we have millimeter-sized walls that we can build up, so they are already very compact and very solid in themselves. On the left-hand side, you can see that we can support different angles. So these are angles that were directly built on top of the powder bed. So you can imagine underneath there was the protective powder bed. And then we could build up to 20 degrees of angles. And that, for example, would not be possible with similar machines as such as the direct energy deposition, because you have no powder bed. Another example in the center is that we can have bridges that are up to 140 millimeter wide, so unsupported, as you can see in the center. So there's one line on the left and one line on the right, and they were combined with these bridges. So there is also another degree of design freedom for you. And one interesting aspect on the right-hand side was the spiral. So there's a center column, and then some millimeters of this column, and then on top there is a freestanding spiral that was built directly onto the powder bed. And that's also only possible because we have such wide area that we are treating with each of the laser beams. And for example, with default SLM, that would not be possible. And for example, you can use this then as a foundation to build on. As you saw earlier, probably, you saw that there's also some oxidation, which is actually normal in most of the additive manufacturing cases. They don't tell you. But then with just some shot peening, shot peening, you could remove the oxide layer. Here you can see my colleague holding the planetary gear for reference, so you can see it's quite large. Here's the same planetary gear. Let's have a look if this video is working. No, it's not. Okay. So you would have seen in this video that the planetary gear is actually moving, and this was printed in one go. So it's not assembled afterwards, it's just printed and cleaned, and then you can already rotate it. So you can actually build rotating large-scale devices with our process. And also here you can see our 10 kilogram macro benchy. I guess most of you are familiar with the benchy. So there you can also see you can build these ramps, you can build bridges, you can build many different structures and still get the benchmark that you wanted. And these, for example, the planetary gear was built in 4 hours, so quite quick. And that had a real build rate of 2.8 kilogram per hour or 350 cubic centimeters per hour. So that's with all the recoating times and so on included. Okay, as I mentioned before, I also want to show you 2 application ideas how we could use this to actually build parts for industry. The first of these would be as a tool. So for example, we can build tools for concrete blocks. Here we are working together in a cooperation with the Cobra Firmen from Germany. So they are the leading producer of concrete molds on the world. And what they produce is these kind of frames. You have the red frame, and inside you have then steel inlets, and these are produced to treat these concrete blocks with very high forces of up to accelerations of up to 30 G, and then also a high dynamic load, and with very abrasive material. And as you can imagine, for these insets and so on, there's a lot of amount of milling to do. So you actually have to remove much more than half of the material, which is a big waste, since we all want to have less waste. As you can see, there is the tamper head that is applying the forces, and then inside this frame you have some insets. And I will show you one example. We were printing one of these corners of the frame structure, which you can see on the right hand side. It's about 300 by 300 millimeters. So that's one of our first demonstrator pieces. The main goal was to reduce the waste, as I mentioned, but what's also very important is to reduce the lead time, because sometimes you have casting, for example, as the main method to produce these frames. And then sometimes you have to wait some months for the casting and then still some weeks for the milling, and then it takes a really long time. But if you could 3D print them, it would be much quicker, especially since most of the tools are unique. So every time you have a different tool. We want to reduce the weight. So for example, we could integrate also some curing channels, some weight reducing structures for lightweight. And then, for example, optional design freedom would also allow us to integrate sensors directly into the frame, for example. Here you can see the demonstrator directly after the printing. And then, as you can see, it was shot peened again. And you can see the lightweight structure. So on purpose, we did not close it with a cover layer so you can see inside. Another application would be, again, the nodes that you saw earlier for custom facades. And as we mentioned before, we were printing them with default SLM, but it was way too slow and way too expensive. So our colleagues designed a new version for our very large machine. Maybe you can see it because it's only 2 or 3 lines of the outline. So it's a very rough design that can be printed rapidly. And here in the center, you can see one of our demonstrators. So that's already connected to the rest of the structure. And for example, through the node, you could lead cooling channels. sensors, cables, whatsoever, because you have this additional design freedom. You can also see the very rough structure. So if you would not want it, for example, you could do some milling, some grinding, but it might even be a nice aesthetic aspect. This is about 250 millimeters high. And then on the right-hand side, you can see an example of how you could integrate it into a larger structure. So it's the same design, it's just the default SLM nodes. So you can see out of these structures that are automatically designed and then printed by us, you could build all kinds of custom shades. Now, let's come back to the comparison between the standard SLM and the Macro-SLM. So we saw before that the standard SLM took about 80 hours for one node and about 1,000 euros without any post-processing, so just the steel and just the argon gas, which is very expensive. And with the Macro-SLM process, we were reducing it from 80 hours down to 5 hours. So you could actually print 2 a day. And then the material cost was down to 150 euros, which is mostly due to the much more affordable powder. On top of that, so that's not including the cost of the machine itself. So on top of that, also the Macro-SLM machine would be much cheaper than the default SLM machine with all the complicated optics, as I mentioned before. Here on the right-hand side, you can also see that we were printing with 3 millimeters offset, because of course our resolution is not as good as the default SLM. So for example, for the surfaces that actually have a function, you have to include some offset. But since you're printing 16 times faster, that's no problem. And this was also printed with 320 cubic centimeters per hour. We remember here it was about 17, so it's still about 20 times faster. So let's conclude. We built for our process a very large build chamber of up to 2 by 1 cubic meters. The powder that we use is a factor of 10 cheaper, which means that all the products are much cheaper and therefore more affordable. Yeah. Also, the setup itself is less expensive because it's a simpler design. The build rate is comparable to the direct energy deposition, which is one of the fastest processes to apply metal 3D printing. The design freedom is similar to the SLM. So you can build all the inside structures, the channels, integrate sensors, and so on. We have above 99% of the relative density. So we are printing dense parts. And also our mechanical properties are above the specifications for bulk material. And as I showed you earlier, we have 2 applications, for example, as tools in the concrete production, or for example, directly printing architectural structures such as these nodes. So thank you very much for your attention.
That's nice.
So thank you, Andreas. Questions from the audience? Be careful, he's a mechanical engineer too. The architects won't understand anything.
That's fine. Thanks for your presentation. With your relatively slow gantry and the large spot size, how do you cope with the residual stresses inside the parts?
With what? Sorry.
How do you cope with the residual stresses inside the parts? Because you're using such a large spot and such a slow movement.
Yeah, that's still an issue. So we still are seeing some residual stresses inside the parts, and then sometimes also deformation, but we are planning to use heat treatment, for example. Or also we are applying a smart algorithm to produce to distribute the energy more. So it's not all in one corner of the part.
Okay, thanks. And the other question, how do you shield it from oxygen? Is there any shielding? Because usually you have it like under argon or nitrogen atmosphere?
It's under an argon atmosphere. So it's we are not filling the complete chamber with argon because it's way too expensive, because it's 4 cubic meters. Yeah, it would have been in the video. Unfortunately, it did not show. But below the laser processing head, there is there's like a hood of argon flow. So it's a local argon atmosphere. So it's not a perfect environment. We are measuring it about, let's say, 0.1% of oxygen still, but it's good enough that you only get light oxidation. But it's a big issue, the argon.
Thanks. So, the usual suspects.
Yeah. Some of the glimpses of the software we're seeing look suspiciously like Prusa Slicer or that family of software. Are those actually suitable tool pathing strategies, or is there custom algorithms underneath?
For some parts of our processes, we are using things like Prusa Slicer, yes, but then we are using them, we are then connecting them to our custom software and hardware. So, yeah, mostly then we are using complex hardware solutions to treat the signals that they're producing.
Okay.
Okay, question from my side. Can you do aluminium?
Yes, we can. I did not include it today because due to the limited time, I might have included it in the end. I did not. Yeah, we can do aluminium.
Okay.
Also
you
with
can
a large
do
scale.
also other alloys stuff.
We also tried case hardening steel, for example, so low alloy steel. So we are trying aluminium, low alloy steel, and high alloy steel, such as 304.
Yeah. Okay. Interesting. There's one.
Very nice presentation. Thank you. I have a question about industrialization of this process. Who do you think will be the clients? Because right now in 3D printing, everything is quite small scaled. Like the metal producers, they're used to a certain range of size, handling, and these type of things. So who do you think will take this technology and bring it to market? Will it be construction companies or welders, or how do you see this?
I think one of the best examples would be tool makers, because as you see, there's quite large tools that are very hard to, or very expensive to manufacture. If you think about forming tools, I don't know, for automotive or things like that. So I think tool makers, for example, could be maybe architecture, but there you might have more norms and.
I can assure you that there are at least 5 to 10 architects in here that want to work with you.
Yeah.
Just because of the scale.
Yeah. That's what we're here for.
But one last question.
The powder bed you're applying, is it reusable afterwards, or is it getting too hot so it loses its, I don't know, Eigenschaften?
We can recycle it. So sometimes there are larger particles forming. We are sieving them and removing them, and then we can recycle the powder bed to fill the machine again. Yeah, because every time if you completely fill it up, it's 20 tons of powder, so you don't throw away 20 tons of steel powder every time.
Very good. All right, then thank you very much.
Thank you.